What's up, everybody? It's Dan from SageMathTutoring.com and back with another video, this time with an AP Calculus problem. I was working on this problem with a student earlier today, and it was kind of taking long to figure it out, so we just decided to skip it, but I did want to get back to it and figure it out once and for all. Interesting problem. Before we dive in, let's cover a couple concepts, though. I made this table, and it's a great table to use if you want to sort of understand the visual relationship between, the second derivative and the original function, the first derivative and the original function, and the first and second derivatives' visual relationship to each other. And really one concept you need for this problem is to recognize that when you're looking for points of inflection, well, what you're looking for is places on the graph of the second derivative such that the function equals 0, but not only that, it has to be these special places on the second derivative graph where the function crosses from negative to positive. So in other words, it goes through the x-axis. That's how you know you're dealing with an inflection point. And as you can see, this top row represents the original function. If you compare the graph of the second derivative to the graph of the original function, clearly we see that as this crosses through the x-axis from negative to positive, the original function goes from concave down to concave up. We call that special point where it changes from concave down to concave up, the point of inflection. The same could be said for when the graph of the second derivative goes from positive to negative through the x-axis. Whenever that occurs, the original function graph goes from concave up to concave down. We would also call that a point of inflection. Now, it's very important for us to recognize that this only happens when the graph of the second derivative goes through the x-axis, okay? We are not interested in when the graph of the second derivative bounces off of the x-axis. We're not interested in those moments. We are instead interested in when the graph of the second derivative goes through the x-axis. So that is concept number one. Anytime the graph of the second derivative goes through the x-axis, it is the case that that represents a point of inflection on the original function graph. Now, the second concept that we need to make sure we're aware of is reminiscent of either Algebra 2 or pre-calc, which is at some point on everybody's math journey, students have been taught that you might end up able to factor polynomial functions thusly, in such a way that might look something like this. And after factoring, you can glean information about what the graph of this particular function looks like. For example, we know that the total degree of the whole function is going to be this exponent of 3 plus this exponent of 2, which is 5, plus this sort of invisible exponent of 1. So that would make the degree of the entire function 6. So the degree of the entire function is 6, which happens to be even. Now, the blue 3 here means that the leading coefficient is 3, and that happens to be positive. Now, hopefully, my student watching and other students watching are recognizing that what that means about the end behavior of this particular graph is that the end behavior would look a little something like that, okay? Now, that's very useful information when you're attempting to graph this function without a calculator. Now, it is also the case that we have a 0 associated with negative 3 here. We have a 0 associated with positive 2 here. We have a 0 associated with negative 10 there. And these are things you should probably plot on the graph right away. So you have a negative 10. There is a point there. There is a point at negative 3, and there happens to be a point at 2 as well. And we already know the end behavior, so therefore we could kind of begin the process of going up like that and going up like that. Now, that's all very useful information. There is this sort of question about what's the graph doing in between, though, and that's when you really have to pay attention to the degree of each factor, not just the degree of the whole thing, but the degree of each factor, and whether or not the degree of the factor in question is odd or even. Now, anytime you have a degree of a factor that's odd, it is the case that the graph goes through the x-axis at the zero associated with that factor. So since the degree here is odd, that means that the graph is going through the x-axis at x equals -10. Therefore, we should feel safe to go ahead and just push that graph through there. Okay, it's going through. Over here, we are looking at an even multiplicity, and we're going to discuss that in a moment. This is an odd multiplicity, so therefore I think we can all feel comfortable saying that the graph will swing back up and actually go through the graph, okay, for the exact same reason that it went through the graph here. It's an odd degree over this factor. This, we have an even degree over this factor. Now, what that means is whenever the degree over a factor is even, it bounces. The graph bounces off of the x-axis. So therefore, it makes sense for us to say that it just kind of grazes at 2, and then it bounces. So that's another concept that will become important for this particular problem. Okay. Now, another concept that is very important for this particular problem is if you have some function, like a parent function called f of x equals x squared, well, many students remember that, oh, that's just a parabola and it's sort of situated with a vertex at the origin. But anytime you have sort of a function, any function really, and then you tack on this +3 at the end, well, that means that you are now shifting the original parent function up 3, and then it looks like this. So we preserve the original sort of shape, the original structure, but we've done nothing more but shift it up 3 units. Now, of course, if we were to say f of x equals x squared, let's say -5, well, that would be the original parent function, which is this black U there, and it goes down 5, so like that, and right there is -5. Okay, so I think everyone watching remembers that is called a vertical shift. Once again, anytime you have a constant sort of tacked on the outside, we call that a vertical shift. Okay, so those really are the 3 main concepts that, in my opinion, are going to come into play into this particular problem. So let's take a look at it. The twice differentiable functions f, g, and h have a second derivative given above, which of the functions f, g, and h have a graph with exactly 2 points of inflection. Okay, so we want exactly 2 points of inflection. First of all, points of inflection. That means that, if we were to graph each of these, which of these would be such that the graph goes through the x-axis from negative to positive or from positive to negative at only 2 places. Once again, if they're asking which of these graphs have exactly 2 points of inflection, it's like saying which of these graphs are such that if you were to graph it, it would go through the x-axis at exactly 2 places. So in my opinion, it might be a good idea to go ahead and graph them, But here's the problem. Doing a rudimentary graph of this one is going to be decently easy, but these are a little tricky because of the +1 and the -1, but here's the deal. You might notice g double prime of x is nothing more than the exact same thing as f double prime of x, except we have a +1 tacked on the end. H double prime of x is the exact same thing as f double prime of x, except we have a -1 tacked on to the end. So in other words, g double prime of x is the same graph as f double prime of x, shifted upward 1 unit. H double prime of x is the exact same graph as f double prime of x, shifted downward 1 unit. So in my opinion, it's probably just going to be a good idea to go ahead and just make a rudimentary graph of f double prime of x. Okay, so in doing so, we're going to have x and y coordinate plane. We are going to have critical values associated with x equals 0, x equals 1, and x equals -2. And by critical values, I mean roots. I mean zeros on the x-axis. So we have a point here. We have a point here. And we have a point here. Now, the degree of this function is even because it's 3 plus 2, which is 5, plus 1, which is 6. So the degree is even. It's also the case that the leading coefficient of this is an invisible positive 1, so the leading coefficient is positive. Whenever you have an even degree and a positive leading coefficient, it is therefore safe to say that the end behavior looks like this. Okay. Now, we have a multiplicity of 3 here that is an odd multiplicity. Therefore, it is safe to say we cut through the x-axis here. We have another odd multiplicity right here associated with the 0 of 0, x equals 0. So therefore, it most definitely would swoop back up and go through. Now, we have a multiplicity of 2 here associated with the 0 of 1, so that means it bounces there. Now, interesting situation. Now, what I've done is I've kind of separated the curve from the graph, okay? We could always put it back, and I think everyone agrees that this is what we would be dealing with. Now, we can see clearly already that this f double prime of x function does indeed have exactly 2 points of inflection because it passes through the x-axis here. Like we said before, that represents a point of inflection, and it passes through the x-axis here. That represents a point of inflection. This is a bounce, so it does not represent a point of inflection. But we need to be very meticulous when we study g double prime of x and h double prime of x. Let's investigate g double prime of x right now. Now, this apparently is the exact same thing as what we just graphed, only +1. So I think my student watching knows that therefore we could say that it's really just this shifted up 1. Kind of like that, you know? Now, if we shifted it that far, well, then there would still be 2 points of inflection. However, if we shifted it this far up, if a +1 shift represented that, well, now there's no points of inflection, right? Because this isn't going through anymore. It might be grazing, but it's not going through anymore. And certainly if we shifted it that far, well, then of course there's no points of inflection at all because it's not even going through the x-axis. So we need to know, did any of those last 2 scenarios happen? So once again, we started here. We need to know if we're shifting it up 1, does that result in a scenario where there's no longer any points of inflection? So we need to kind of investigate that. So in my opinion, the best way to investigate that, now there could be a better way. Maybe there's a really easy way that I'm missing. But in my opinion, the best way to investigate that is find a point that's somewhere over here. And then plug the x value of that point into this G double prime, okay? Because let's be very clear, this right here is F double prime, but we're investigating G double prime, which is the same as F double prime, but it's plus 1. So my thought is, what if we found an X value here, for example, -1, and if we plugged that into this one, if this point is still negative, then we know that G double prime also has 2 points of inflection. Now you might be wondering, why is that? Well, the reason is because if we were to investigate that, if we still have some kind of a negative value, negative y coordinate value here, well, then we know that it's still the case that it's crossing through here and it's crossing through here. So if after plugging in that special test x value here, we still end up with a negative y value here, then we know that we have, in a sense, preserved the points of inflection, okay? So let's do that. Let's go ahead and shift this up, and we're going to keep our fingers crossed. We're going to see if this graph looks kind of something like this. So I say the perfect x value to test, honestly, is a -1. So when we plug in -1 here, we get -1 times -1 minus 1 squared, -1 plus 2 cubed plus 1. And after that, it would be -1 times -2 squared times 1 cubed plus 1. And that would be -1 times 4 times 1 plus 1. And then that would be -4 plus 1. And that indeed would be -3. So it turns out that after plugging in that special test value, this point right here is -1, -3. And the fact that that y coordinate is negative means that this is still under the x-axis, which means that it crossed through the x-axis here, therefore inflection point, and it crossed through the x-axis here, therefore inflection point. So far, we know that the graphs of f double prime of x most definitely has exactly 2 inflection points, and we have also seen that G double prime of x most definitely has exactly 2 inflection points. So that's good. Let's take a look at the answer choices. This one says that it's G only. Well, we know that's wrong. This one says H only, so we know that's wrong. This one says F and G, so that could be the case, but this one says F, G, and H. So, of course, now we have to look at H double prime. So looking at H double prime, now we will be using a very similar reasoning process. Well, the same reasoning process, but some slightly different details now. Okay. Once again, this right here is the graph of F double prime, okay? So we have the graph of F double prime here, and we know that H double prime is going to be the exact same thing, except we're shifting down a little bit, like that. All right? We're shifting down. Now, imagine we shifted down that much. Well, guess what? In that moment, we would have a point of inflection here, that's 1. We would have a point of inflection here, that's 2. And then we would have 2 more points of inflection there, right? If we were to shift down like that, well, we would have 1, 2, 3, 4 points of inflection. So that would certainly demonstrate that we no longer have exactly 2 points of inflection, and therefore this does not work, okay? But here's the weird scenario I really want to draw your attention to. What if after shifting it down 1, the graph ended up looking like this? Well, that would be 2 points of inflection, right? So now we have to go on this separate mission to see how far down this original graph shifts. Is it shifting down just a little bit, in which case there are 4 points of inflection? Or is it shifting down so much that there are 2 points of inflection right here? So then you might be wondering, what the hell should I test now? Which value should I test? Well, we should test this value, because imagine we test some point like around there, the green point. Well, isn't it the case that if we started with the original function of f double prime of x, and then we shifted it down 1, if it's the case that that green point is still above the x-axis, well, then we know there's 4 points of inflection. And of course, in that case, this one is not part of the answer to this problem. But if it's the case that after shifting this down so far that the green point is below the x-axis, aka the y-coordinate of the green point is negative, well, in that moment we would at least have a sign that there could be 2 points of inflection. Okay, there could be 2 points of inflection. So I say we test it out. I say we look at it. Now, let's be very clear. Once again, we started here. If it turns out that after nudging it down a little bit, if it turns out that we have any positive y value associated with this part of the graph, then it's impossible for this to have exactly 2 points of inflection. All right, rewind the tape as much as you need to verify that for yourself. We start here. If you shift it down, but that green point is still above the x-axis, guess what? We have more than 2 points of inflection. So what do? Well, we pick a point, an x value, like 1/2, and we plug it into this. And if we get a positive value, then it's going to be more than exactly 2 points of inflection. So I'm probably talking too much. Let's just dive in. I think you agree we're looking at this. Beginning the process, we have 1/2 times 1/2 squared times 2.5 cubed, which is really 5/2 cubed. And that's that. So we have 1/2 times 1/4 times, 125/8 minus 1. So we're looking at 1/8 times 125/8. Let's just call this minus 1 for now. We have 125/64, and let's just call this minus 64/64, and that would give us a positive number, right? So that would be this, I think, over 64. So that gives us a positive number. Yeah, am I right about that? Yeah, I'm right about that. So that's the fact that this is positive is the most important thing. So there is no question that upon moving this down 1 unit, upon moving this graph down, it ended up in a situation where there was still this positive stuff happening there, and then therefore, lo and behold, 1 point of inflection, 2 point of inflection, 3 point of inflection, 4 point of inflection. So H double prime is not included in the answer. Now, I am not sure if there's a better way of going about that without a calculator. I mean, if you were using a calculator, well, then you could just graph everything, right? But without a calculator, as far as I could tell, that's the best way to go about this. So hopefully that makes sense for my student who's watching this from home. Yeah, good luck with this one. Maybe ask the teacher a couple questions about this. But everything I did was very sound reasoning. The only question is there some kind of a trick involved that makes the whole process faster.